Welcome back to mathkernel. We can build orthonormal bases now, and we can read a bilinear form off a matrix. Today we ask a single geometric question. Given a subspace, what is everything perpendicular to it? And we answer it 5 times over. The note calls this section exam mandatory, and every proof in it runs on the exact same move. Here's the object of the day. Fix a subspace U. Its orthogonal complement, written U perp, is the set of every vector in the whole space that is perpendicular to every vector of U at once. Not perpendicular to one vector, perpendicular to all of them simultaneously.
So on the board, U is the blue line span of V, and U perp is that green line crossing it at a right angle?
In the plane, yes. But let me lift it to 3 dimensions, because that's where the picture really speaks. Take a single vector V. Everything perpendicular to it isn't a line. It's the entire plane through the origin at right angles to V. That plane is span V perp.
And if U is spanned by 2 vectors?
Then you're asking for everything perpendicular to both at once, and that collapses down to a single line, the cross-product direction in 3 dimensions. More constraints, smaller complement.
Hold on. The definition says perpendicular to every vector in U. U has infinitely many vectors. Do I really have to check all of them?
You don't, and that shortcut is the whole engine of this topic. If W is perpendicular to each basis vector of U, then bilinearity spreads the product across any combination of them. So W is automatically perpendicular to all of U. Test the basis, get the rest for free. So U perp is everything at right angles to U, and thanks to bilinearity, you only ever check it against a basis. Hold that shortcut, every proof today leans on it. First property, and it's my favorite because the proof is 2 lines. How much can U and U perp share? The answer is nothing but the 0 vector.
On the board, the 2 lines only touch at the origin, that green dot. So geometrically, it's obvious. But why in general?
Suppose some x sits in both. Being in U perp means x is perpendicular to every vector of U. But x is also in U. So x is perpendicular to a vector in U, and that vector is allowed to be x itself.
So you feed x its own vector, is perpendicular to itself.
Exactly the move. Set V equal to x, which is legal precisely because x lives in U. That gives the scalar product of x with x equal to 0. And positive definiteness of the scalar product says the only vector with 0 length squared is the 0 vector. So x is 0. So the only vector perpendicular to its own home is the 0 vector. U and U perp meet at the origin and nowhere else. Remember the phrase set V equals x? That's the move the whole proof turns on. Second property. No matter what U is, U perp is guaranteed to be a subspace. It contains 0, and it's closed under addition and scaling.
Wait, you said no matter what U is. Are you telling me U itself doesn't have to be a subspace, and the complement still comes out 1?
That's exactly what I'm telling you, and it's the surprise worth pausing on. You could be a random scatter of vectors, the gray dots on the board, not a subspace at all. Yet the set of things perpendicular to that scatter is a clean subspace every time.
How does that happen if U is such a mess?
Because the definition only ever asks about the second slot of the scalar product. First, 0 is perpendicular to everything, so 0 is in. Then take 2 vectors W1 and W2 in U perp, the green and violet arrows, and any scalar. Bilinearity in that second slot splits the product of V with their combination into 2 pieces, and both pieces are already 0.
So the combination is still perpendicular to V, and V was arbitrary.
Right, and saying V is arbitrary at the start and again at the end is the part that makes it airtight. Since it holds for every V in U, the sum and the scalar multiple land back in U perp. All 3 axioms. All from bilinearity in the second slot. So you can be shapeless, But perpendicularity always launders it into a subspace, because the closure lives in the scalar product, not in you. Now two structural facts, and they share a chapter because they're both about how complements behave as you move subspaces around. First, monotonicity. If W sits inside U, then U perp sits inside W perp. The inclusion flips direction.
Flips? That feels backwards. Bigger space, bigger complement, surely?
The opposite, and here's the intuition. To be in U perp, you must be perpendicular to all of U, a heavy demand. To be in W perp, you only need to clear the smaller set W. Fewer things to be perpendicular to means an easier club to join, so W perp is the bigger one. Anything that cleared the harder bar already clears the easier one.
So more constraints, smaller complement. Fine. And the proof is just restrict to the part?
One line. If W is perpendicular to everything in U, then in particular it's perpendicular to everything in the subcollection W. So W is in W perp. Done. Now the second fact, the double complement. Take the complement twice.
And you'd hope you land right back where you started, at U.
You always get at least U. Every vector of U is trivially perpendicular to everything that's perpendicular to it, so U sits inside its double complement in any dimension. But full equality, getting exactly U back, needs finite dimensions, where the counts line up. Dimension of U plus dimension of U perp equals dimension of the whole space.
And in infinite dimensions that count can fail, so you only keep the one-way inclusion.
So, shrink the subspace and the complement grows, and in finite dimensions complementing twice is the identity. The dimensions leave no room for anything else. Enough theory, let's actually compute one. Working in 3 dimensions with the standard scalar product, take V equals 3, 4, 1, and W equals 5, minus 3, 3, from the notes exercise.
And the recipe? How do I turn perpendicular to U into something I can solve?
You stack the basis vectors of U as the rows of a matrix A. A vector W is in U perp exactly when its scalar product with each row is 0, which is precisely the equation A times W equals 0. So U perp is the kernel of that matrix. Gaussian elimination, and you're done. Warm up with just V. One row means one equation. 3x1 plus 4x2 plus x3 equals 0. That's a single plane, 2 free variables, so span V perp is 2-dimensional, spanned by 1, 0, minus 3 and 0, 1, minus 4.
Now both V and W. 2 equations in 3 unknowns. Isn't there a faster path in 3 dimensions than grinding the system?
There is, and it's the reason 3 dimensions are special. When U is a plane spanned by 2 independent vectors, its complement is a line, and the cross product hands you the direction of that line directly. Compute V cross W, and you get 15 minus 4 minus 29.
And that single vector really is perpendicular to both.
Check it. V dotted with it is 45 minus 16 minus 29, which is 0, and W gives 75 plus 12 minus 87, also 0. So the complement of that plane is the line it spans, and the dimensions check. 2 plus 1 makes 3. So, rows are the basis, the complement is the kernel, and in 3 dimensions a plane's complement is just one cross product away. Let's gather it. U perp is everything perpendicular to U, and 4 facts pin it down. It meets U only at 0, it's always a subspace, it reverses inclusions, and complementing twice returns U in finite dimensions.
And each of those proofs was the same move, take an arbitrary V, use bilinearity, and for the intersection, feed X to itself. Fine, I can prove it and compute it. But what's it actually for? Why do I want everything perpendicular to U?
That's exactly the next video. The whole space splits as U plus its complement, and that direct sum is what lets you drop any vector straight down onto U, the orthogonal projection. It's the closest point in U, the best approximation, and the error is precisely the U-perp part. So today we built the perpendicular half of the space. Next, we use it to measure distance, the closest point in U, and how far off you were. That's the orthogonal complement. Everything perpendicular to you. 5 short proofs that all run on one trick, and a matrix kernel to compute it. Thanks for watching. The perpendicular half of the space is yours now. Next time we put it to work measuring distance.